Henderson Hasselbalch equation. And this equation just simply says pH equals the pKa minus the log of the acid concentration divided by the base concentration of a solution. And I deliberately put that in brackets because when you do calculations, this is the first thing here. This thing here is the first thing that you need to calculate. Acid over base, this ratio. And then you take the log of that. Yeah? And then from this number that you get, you use that and subtract that from the pKa. Then you get the pH. So these are basically the steps that you want to do when you do these calculations. I told you that with this Henderson-Hasselbalch equation, we get a relationship between the pH and the acid-base ratio. So in a way, the pH determines the acid-to-base ratio. Okay? But also, we can turn this around and we can say the acid-to-base ratio determines the pH of a solution. So, in other words, by messing around with this acid-to-base ratio, we can establish a certain pH in a solution. And this is very often quite useful because for certain reactions, we want to have a fixed pH. We want to have a fixed proton concentration. Just to give you an example, if you have, let's say, a protein, you've done proteins in BI308 already, haven't you? So let's say you have a protein, like that, nicely folded into its active structure, and all of a sudden you have too many protons in it. What could happen? It denatures. The protein loses its nice structure and end up maybe with something like that. Right? Screwed up chicken. So, if we don't want that, we have to avoid that there are too many protons around. So we have to fix the pH in our solution. And we can do that by playing around with the acid-to-base concentration. So, let me give you an example. Let's say we have, let me write the Henderson-Hasselbalch equation again. pH equals pKa minus log acid to base. And let's say I have the same amount or the same concentration of acid as I have concentration of base. Can you tell me which pH we would get? Anton?
We use
You mentioned the word buffer, obviously, yes. Why is it, you're absolutely right, but why is it from the Henderson-Hasselbalch equation, why is it that what you said, pH in this case equals pKa? Why is that the case? You have log of acid to base, and that is, if they are the same, the ratio would be 1 to 1, basically. Yeah? That makes sense? 1 divided by 1 gives 1. Log of 1 gives you 0, obviously. So we have pH equals pKa. So let's say the pKa, in this case, would be 7. It's a very weak acid. You can tell that it's a weak acid because pKa, for weak acid, we said pKa high or low? Where do I stop? High or low? I get a sore arm here. Help me. Is it low? What does a pKa say? pKa is what was it defined as? Minus log of Ka. What the heck is Ka? That was the equilibrium constant, or in this case, the dissociation constant. So, and we said if we have a high Ka, we have a low pKa. A high Ka means lots of it is dissociated. So high Ka is a strong acid. And high Ka means low pKa. Yeah? Or conversely, Ka is low, it's a weak acid. And if the Ka is low, what is the consequence for the pKa? pKa is high. So pKa is high. So here I have a pKa of, let's say, as I said, 7. Strong or weak acid? High pKa, low Ka, weak acid. Yep. Right, so if our acid to base ratio is 1, then the pH of the solution is the same as the pKa. So, for example, I can take, let's say, 100 millimolar acid, bless you, and I add 100 millimolar of the corresponding conjugate base. So I have the same concentrations in it. How much of the substance do I have in it, in my solution, in total? Let's say I have a liter, 1 liter, with 100 millimolar acid and 100 millimolar base. How much of the things do I have in it? Don't need a calculator for that. Sorry? The total volume is 1 liter. Yeah? And I add 100 millimolar of the acid, let's say 100 millimolar of acetic acid, plus 100 millimolar of sodium acetate. How much of the acetate do I have? Loud? No. You have. These are the black ones are your acids. Yeah? And the red ones are your acetates. How much of the acetate containing stuff do I have in it? 100 millimolar plus 100 millimolar. So a total is 200 millimolar. Simple. I don't do difficult. Right? So we have a 200 millimolar solution. 100 millimolar is made up of the acid, and 100 millimolar is made up of the base. Does it make sense? So you have 1 part acid, 1 part base. It's a little bit like mixing a drink. Pina colada. What's in pina colada? Loud? Rum. What else? Pineapple juice. What else? Coconut milk. Yeah, exactly. So, don't get me wrong. I don't want to turn you into alcoholics, but you have different recipes for pina colada. So you have 1 part rum, 1 part pineapple, let's say 2 part coconut milk. Okay, how many parts have you got? 4 parts. Let's say you want to make 400 milliliter of your brew. What do you need? So you get how many rum? 100 milliliter. Pineapple juice? 100. 2 parts? 200 milliliter. Gives you 400 milliliter, right? So that's the parts thing. Why do I do that? Because I like pina colada, yeah. But there's a reason for that. Let's go back to this Henderson-Hasselbalch equation. Let's say we have, or you tell me, what is the pH if we have pKa minus log acid over base? What would happen if we have 1 part acid and 10 part base? What do we get? Obviously not pina colada, but what would we get in this case? Anton says pK plus 1. Is he right? Don't trust him just like that. Nothing against you. Of course I trust you, but, never trust anyone. When I tell people that I don't trust them, they get easily offended. But I say to them, look, I don't trust myself. How less can I trust anyone else? So, yeah. Okay, let's see how it works. pH equals pKa minus log 1 part acid over 10 part base. This gives us log of 0.1, 1 over 10 in this case, minus log 0.1. 0.1 log gives us -1. Yeah? And therefore, we have pH equals pKa minus times minus gives plus. So it's pKa plus 1. Or in other words, let's say our pKa is 7. What's the pH? 8. So if we add more base than acid, we would expect the pH to go up. So here, in this case, pH must go up. What would happen if we have 10 times acid and 1 times base? So if you said we get pH equals pKa minus 1, you are absolutely right. You add more acid, and therefore the pH goes down. Does that make sense? How many parts actually do you have in your drink? 11 parts, yes? That's quite important. We have together 11 parts. Don't forget that. It's 11, not 10. Okay, but hey, who cares about this stuff? Do I really give a damn about whether the pH goes up or down or stays the same, or is the pKa or something like that? What is the practical use of this stuff? Let's do a little example with that. Let's say I have a pot here with about 1 liter of water in it. Okay? What is the pH of water? So we've got a pH of 7. Right. Nice and neutral. Life is good. Can stick my finger in. Here, I have a little pot in which I have one molar hydrochloric acid. Okay? 1 molar hydrochloric acid. What is the pH? pH is 0. Would you like to stick your finger in that? No. If you leave it in for some time, there won't be much left of the finger. It sizzles probably a little bit. It burns like hell. Trust me, I've tried that once. It wasn't a terribly pleasant experience, but, you know, YOLO. Okay, now what we do is we take 10 milliliter of this 1 molar solution and put that in our 1 liter of water. Can you envisage that? Just take 10 milliliter of that, whack it in. What happens? Sorry?
It becomes diluted.
The acid gets diluted. Yeah, that's right. What happens to the pH? It changes. The pH goes? The pH goes? Down or up? Down. Okay, pH goes down. So if we do that, pH goes down. Yeah? In our, I should probably do that here, pH goes down if we add the acid. Can we actually calculate how much the pH goes down? How could we calculate that? Any suggestions? Think about it. Think about this as a potential exam question. How do you calculate how much the pH goes down by? How would you do that? How would you tackle this problem? Remember what I said, it's all about mole. Aha. How would you do that?
You could use like volume and concentration to account moles.
Yes, you could, in the first place, you could figure out how many moles of protons have I transferred. Yeah? How many moles of protons go from here into here? So we can say we want to know how many mole protons are in 10 milliliter of a 1 molar hydrochloric acid solution. And you've done that before. Yeah? Let's do it with dimensional analysis. What is the unit that we are looking for? Mole. Do we have mole anywhere? We have it in 1 molar. That means 1 mole. What does it mean? 1 mole? 1 mole per liter. Now the mole is good, but the liter, I want to get rid of that. Do we have liters or anything like that? Aha, we have the 10 milliliters, so times 10 to the minus 3 liters. Yeah? The liters cancel out. And I have left 1 times 10, that's 10 times 10 to the minus 3 mole. Does that make sense? So I take 10 times 10 to the minus 3 mole, and I put them into this 1 liter. What is my volume now? It is 1010 milliliter, because we have 1 liter in the first place, and we add 10 milliliter, so that would be 1.01 liter. Does that make sense so far? So that is my proton concentration in here. 10 times 10 to the minus 3 mole divided by 1.01 liter. Let's do this calculation quickly. What do we get in terms of molar concentration for this guy? 9, so that gives us 9.9 times 10 to the minus 3 molar. Can we do the pH now? pH equals minus log of this. Minus log of this. And that gives us roughly 2. Yeah? Is that right? 2? Aha. So, by transferring 10 milliliters of this 1 molar hydrochloric acid, our pH shifts from pH 7 to pH 2. Okay? This is a change of 5 pH units. We have a change of 5 pH units, or in our proton concentration, a shift of factor of 100,000, 10 to the power of 5. Yeah? Okay, so that was the first thing that we calculated. Now, let's do something. I need my notes for that because I can't remember the numbers. Let's say we have a similar scenario. We have 1 liter but this time let me quickly check that I don't say anything stupid. But this time, we have an acid and a base in it, at a mixture at a ratio of 1:1. And to make life easier, we have 0.1 molar of acid and 0.1 molar of base. And let's say we have a pKa of 7. Okay? What is the pH of our solution here? Loud? 7. Why? pKa minus log, and we have 0.1 molar, 0.1 molar. This gives 0, so we have pH equals 7. Yeah? Exactly right. Now that is exactly the same that we had before when we used our water. We have a pH of 7. Nice and smooth. Stick your finger in, yes or yes? Yes, no problem. Won't dissolve in a hurry. So it's good stuff. What we do now is we have our 1 molar solution of hydrochloric acid. What was the pH again? pH 0. And we do the same thing as before. We add 10 milliliter of that. How is the pH going to change if we do that? First of all, will it go up or down? Will it be higher than 7 or lower than 7? Lower than 7. Why lower than 7? Because we add an acid. Yeah? So the pH must go down. But how much is it going down? Can we calculate that? How much of the protons do we add? Well, we've just done this calculation, haven't we? So we add, again, we add 10 times 10 to the minus 3 mole. I can write this as 10 millimole. We've just done this calculation, yeah? So we add 10 millimole of protons. Now, what is going to happen to the acid and the base in our solution? Let's look at the acid at the base first. So we have the base, and the base catches the protons that we add. Yeah? And what happens to the base plus the protons? What is that? That's the acid. Exactly. So we convert the base by adding protons into the acid. What is the consequence of for the base? If we start with, say, 100 millimole of base, we add 10 millimole of the protons. How much of the base do we have left? How much of the base are we left with? We have 100 millimole of the base. Then we add 10 millimole of the acid. How much of the base is left? 90 millimole, right? So that gives us 90 millimole of the base that's left then. Because 10 millimole have been nicked by the protons. Let's say we start with 100 millimole of the acid. How much of the acid have we got left if we add these 10 millimole of protons, which are then nabbed by the base? 110. We have 110 millimole acid. Yeah? Does that make sense? Now, obviously, we need to calculate how many mole acid and how many millimole base we have in our solution here. Can we do that? This was just an example with the 100, just to illustrate the concept. We said we have 1 liter of 0.1 molar acid solution. How many moles is that? Can we do the calculation? Well, we do that with a dimensional analysis again. Mole, we have 0.1 mole per liter, and we have 1 liter, so that gives us 0.1 mole. And I can write this, how many millimoles is that? 100. So that's 100 millimole. Oh, look at that. I just chose, by serendipity, I chose the right numbers in the first place where I illustrated that to you. So I've got 100 millimole of acid. And obviously the same for the base, 100 millimole of base in my 1 liter. I add my 10 millimole of protons, and I get 110 millimole of acid and 90 millimole of base. Yeah? pH equals pKa minus log of these ratios. Do I actually have to worry about the volume? Theoretically, I need to worry about it because I have this 110 millimole acid in 1.01 liter. Loud? It cancels it out because I've got the base also in the same volume, 1.01 liter. Yeah? So I don't really have to worry about it. So we have a new pH. pH equals pKa minus log 110 over 90. pKa was 7. Minus log 110 over 90, what is that? It's 11. It's 11 by 9, yeah? 1.2. Good? 1.1. 1.2. Okay, good. I buy that. What is log of 1.2? 0.07 or 0.079. Let's do 8. Yeah. So pH equals 7 minus 0.08 is 6.92. Is that right? 6.92. We started with a pH of 7. We added our hydrochloric acid, and we got a pH of 6.92. The pH difference is 0.08. The only difference was, if you remember, earlier on, we did that with pure water. The difference in pH was 5. 5 pH units. Now, with this little trick, We added the same amount of acid, but we only got a pH difference of 0.08. Would you stick your finger into the solution of pH 6.92? 6.92, yeah? That's pretty safe. Would you stick your finger into a pH solution of pH 2? Definitely not. You see what this acid and base in the solution does. It actually buffers the solution against any changes. That is why a mixture of acid and base is called a buffer. Sorry, conjugate base, yeah. That's true. And conjugate base. So these buffers, the function of a buffer is to make an environment stable against pH changes. Yeah? You have used a buffer before, haven't you? In one of the practicals. You used a phosphate buffer and a borate buffer. These buffers make sure that in your reaction, the pH does not change dramatically. Here's another thing. Where else would you want to have the environment pretty constant? Where do you want that? In your body, exactly. So, for example, what's the pH of blood? pH of blood. Anyone? 6.8. I come back to that. It's close. 7? 6.7. It's slightly in the alkaline. pH of blood is around 7.2. Yeah? So it is neutral, it is in the neutral range, but it is slightly alkaline. Now, what you said with 6.8 and 6.7, if your blood pH drops to 6.8 or even lower, 6.7, you have what is called an acidosis, exactly. And within a couple of hours, if it is not treated, you are dead. Likewise, if you have a blood pH of 7.6 or above, untreated, you have an alkalosis, and in a couple of hours you are dead. Yeah? Which is usually very inconvenient if you are dead. So, what you have to ensure is that your blood is always maintained at the right level, say 7.2. And therefore, you have buffer systems in your blood that make sure that the pH, even when you do silly things, for example, what could make your blood acidic? Sorry? Drinking vinegar, yes, actually. Good point. A rather unpleasant way of committing suicide is injecting pure hydrochloric acid into your veins. It starts to sizzle, and then your pH changes so dramatically that the buffer system can't cope with it. Yeah? So that's, my advice would be don't. Don't try that at home. What else? Less dramatic.
No.
Sorry?
No,
Change the pH. Look, guys, I'm not giving you any instructions to do it.
The trouble of injecting hydrochloric acid, we can just inject oxygen.
What happens if you inject oxygen? Oh yeah, you start fizzing. You get bubbles in your arteries, and that obviously blocks the blood flow to the brain and the heart, and that's still, it's not a good thing. But we are not talking about suicide, please, right? How else could you change the pH in your blood? The CO2 concentration, or, oh yes, I need somebody here. Are you fit? Are you healthy? Okay, can you stand up for a moment? What happens? He is producing lactic acid in his muscle. Thank you very much. I don't want you to keel over. He's producing lactic acid in his muscle, which increases the pH in his blood. Another thing that some people are suffering from is if you cannot use glucose properly, and for your energy requirements, you have to resort to getting energy from other sources like fatty acids. So you break down fatty acids into all sorts of other metabolites, and most of them are acidic. What do you call this condition if you can't use glucose properly?
diabetes.
It's diabetes, right? In the case of diabetes, you are constantly battling with too many protons in your blood, and the buffer system in your blood is fighting it so that it does not get below a pH of, say, 7.1, which is considered acceptable. Yeah? Likewise, you can reduce you can make your blood more alkaline very easily, because as you earlier said, we have a fantastic buffer system in the blood. This buffer system consists of actually carbonic acid, H2CO3, and the base HCO3 minus. So in the blood you have the acid and the base. And this acid actually is not carbonic acid as such, it is the same as carbon dioxide. So if you remove the carbon dioxide from the blood, you reduce the acid concentration in the blood. If you have less acid in the blood, what is the consequence on the pH? Less acid, more base, means the pH goes up or down. It goes up, exactly. How can you remove the CO2 from your body? You hyperventilate. Yeah? When you are going into an exam, you start hyperventilating. What happens? pH in your blood goes up because there is no longer enough acid there. The horrible thing is there is a mechanism that triggers the release of adrenaline, the fight and flight hormone, when the blood gets too alkaline. So you start hyperventilating because there is this bloody exam, and as a consequence, there is a release of adrenaline, which then leads, it's a positive feedback mechanism, which leads to stronger hyperventilation, and eventually you passing out. So next time you go in an exam or have a stressful situation, think about that. What do? Breathe slowly, or breathe into a bag, into a paper bag, because then you regain the carbon dioxide and you establish the right pH again. You see how incredibly important it is to have these buffer systems. Does that make sense? I will post a video that goes a little beyond that, that shows you how your body actually adjusts to changes in the internal pH. And it's definitely worth looking at, especially for the biomed people, because that's really interesting stuff, but it's not going to be assessed. Have a lovely weekend, and I shall see you on Monday.